Okay, this presentation is about scientific notation, specifically how to solve problems involving very large or very small numbers, but I'm going to start with a review. Remember from previous lessons that scientific notation is just a short way to write very large or very small numbers, and it follows this format. So some number times a power of 10. The sum number, so this part right here, has to be greater than or equal to 1 or less than 10. In other words, there can only be one number before the decimal. This power of 10 tells us how many times we would have to move the decimal before we got to our original number in standard form. So standard form, again, is the same thing as decimal form. It's what we are used to numbers looking like. So to express each number in standard form, we have to find our decimal, which is right here. We have to look at the exponent and move it that many places. If it is a large number, then remember it is going to be a large number here. So an exponent greater than 1, it's going to be a large number. Less than 1, it's going to be a small number. So if it's a small exponent, small number. So this tells us we have to move the decimal 7 places. So I tend to do my loops underneath 1, 2, 3, 4, 5, 6. And if there's not a number there, we use a placeholder. So, and we want to write it nice and neat so people can read it. 7, 8, 2, 1 with 3 zeros. And then put your commas in so it's easy to read. So 7,821,000. And I always double check my counting. If it's here, 1, 2, 3, 4, 5, 6. That matches. The second example, it is going to be a small number. So I know that I'm going to move my decimal this way, 1, 2, 3, 4, 5 places. Putting in my zeros, that would get me 0.000083. Going the other way, you first have to decide where you're going to stop your decimal. It's going to go right there between the 1 and the 2 because remember that first number has to be between 1 and 10. And then you're going to take that times a power of 10. And the exponent tells us how many places we'd have to move the decimal. The decimal is right here, so to get it between the 1 and the 2, you'd have to move it 1, 2, 3, 4, 5, 6, 7 places. And it's going to be a positive exponent because it started as a big number. I always double check. 1, 2, 3, 4, 5, 6, 7. That matches. This one, on the other hand, starts as a small number. So I'm going to find where I'm going to put my decimal. Again, there has to be just one number, non-zero number before the decimal, times 10 to the, and then we're going to count. I had to move it 1, 2, 3, 4, 5 places. But remember, it is a negative because I started out with a very small number. And double check yourself. 1, 2, 3, 4, 5. So that works. A very quick review on multiplication and division with scientific notation. Remember, because of the associative property and commutative property, since these are all multiplication in here, we can rearrange and multiply in a different order. So I'm going to put my numbers next to each other, and I'm going to put my powers of 10 next to each other. So 1.5 times 7 is 10.5 times 10 to the, and remember, if we're multiplying powers with the same base, we add the exponents. And if you stopped here, this would be wrong because this is not in scientific notation. We have one too many decimal places. So I'm going to move my decimal here. I'm going to talk about this in a couple different ways because how will that change my exponent? So a rule of thumb is if you make your number smaller, I made it 1 smaller, I have to make my exponent 1 bigger. Another way you can do it is think, okay, it's here. To put it in standard form, I'd have to move it this way 7 places. To get it back into scientific notation, I'd have to move it back to the left 7 places, but plus 1 more, so 8 places. Or you could actually write it out in standard form and then re-put it into scientific notation. But this is our final answer. With division, again, you are just grouping the numbers. 1.3 goes into 2.6 2 times, and if you are dividing powers with the same base, you subtract 5 minus 8 is a negative 3. All right, let's get to some application problems. The number one thing with application problems is pulling out the numbers and knowing what to do with them. So really it is today going to be about, do you multiply or do you divide? So what I suggest you do is always change the scientific notation into easier numbers to work with, figure that out, and then do the scientific notation. So put it into easier numbers to decide if you're multiplying or dividing or adding or subtracting. Because once you get into scientific notation numbers, it just adds that element of it looking way more difficult than it is. So the first problem, my vacation spot is 1,200 miles away. How long will it take me to get there if I'm traveling at an average speed of 80 miles per hour? Well, we know what to do with distance equals rate times time problems. Distance equals rate times time. So I'm going to put my distance in for D, my rate in, and I'm going to solve for time. How long will it take me? So it's a really easy problem when you have easy numbers. And many of your problems today are like this. So I divided by 80 on both sides, so the time it's going to take me is unfortunately 15 whole hours before I can get to my vacation spot. All right, next example. There are 60 people in a room with an area of 120 feet squared. What is the population density? And then it gives you a hint right here, people per square feet. So again, if this was in scientific notation, if we had tons and tons of people in a very large area, this would be difficult. But this really gives us a clue. We're talking people per square feet. So that per means that we're dividing the people by the area. So that gives me, I'm going to leave it in fraction form, 1 person per 2 square feet. So pretty tight fit. All right, let's try one of these. And please understand that I know just by watching a few problems that you're still probably going to struggle through that problem solving, but that's why it's called problem solving. So you have to work through it. Think about it with easier numbers. So here, the speed of light is approximately 3.10 to the 8th meters per second. How far does it travel? In 4 times 10 squared seconds. So if you just ignored this part and think, okay, I can do this. This is about how far, speed, distance equals rate times time. I've done many of these. The speed, that's the rate, 3 times 10 to the 8th. How far, so I'm looking for my distance, and this is my time. It becomes a really easy problem. So a lot of the problems today have to do with distance equals rate times time. So I'm going to multiply them. Remember, we multiply the numbers, and then we multiply our powers of 10 by adding the exponents, 10. So now I have 12 times 10 to the 10th, but this is not in scientific notation because the decimal is in the wrong spot. It's right there. It needs to be here. So we needed to make our number 1 smaller, 1 place value smaller, So we needed to make our exponent 1 bigger. Or the other way to think about it is I needed to go this way 10 places to get it into standard form, and then to put it back into scientific notation, I needed to go that 10 plus one more spot. So 1.2 times 10 to the 11th meters is how far it would travel in that number of seconds.